Okay, let's start. So now it's time to summarize the course and for you to prepare for the exam. So I can start by mentioning that on the home page there are, I have now uploaded detailed learning outcomes. So it's 3 pages with quite detailed learning outcomes of what you're expected to know for the exam. There are also a collection of old exam problems, and there are 4 old exams as well. So I hope there should be, from this you know what to expect for the exam. Then I can mention that the exam, so since the character of this course is that we have talked about quite many different aspects when building embedded systems. So what we will do is that in the exam you can also then expect different kind of questions for the different areas. I mean scheduling, temporal logic, etc. In general people do rather well on the exam. So it's not a hard exam in comparison to courses where you have one theory that you dive into and then you go deeper and deeper and deeper. So we have a couple of different areas that you need to understand. This is also the last year that we have the exam, so for the next year we will skip the exam and try to examine this throughout the course instead. It's my aunt. Hey. Okay. Now I lost. Okay, over to my first slide then. The exam is on May 31st. In the afternoon, SB Multisal, Samhällsbyggnadsteknik. I will be in Italy when this exam. So that will be one of the TAs to show up and ask a question for the exam. So what you can bring with you is the normal stuff, but you can also have one A4 sheet with handwritten notes. You're allowed to write on both sides. You can also bring with you the Essential C. You're not allowed to have any comments in the report, but I got a question about if a marker pen is okay. So if you would like to highlight something, that's okay, but you're not allowed to write any text or something like that. And you can also, if you like, bring a dictionary with you. So how to study for the exam? So we don't really have a course book in this course because we cover so many different areas that there is no book that fits the course very well. So basically the lecture notes, I've tried to upload all my lectures and all the material I have. So I think that is the primary resource for you. There are some background online free books that we can refer to that you can go and have more background material if you like. But apart from that, I think there's learning outcomes. So that is very detailed. Go and look at that. Try to search for the answers in the lectures and possibly also in the background if that is needed. You have all the example problems to know a little bit what to expect and old exams. So if you have gone through this, you will be well prepared for the exam. When it comes to the learning outcomes, as I said, this will just be a short overview of the more detailed that we have in this document at the homepage. But basically, as I see it, so this course, here we try to bring, so you have to use some knowledge from the discrete event systems course, some knowledge from the modeling and simulation, some knowledge from the linear control system, and then you have to apply that together with some new knowledge that we have taught in this course. In particular, the implementation aspects with the real-time operating systems and the scheduling and specifications and that. Yeah, and we started the course by talking about hybrid systems. So because you have talked about continuous systems in the modeling and simulation, you have talked about discrete event systems. And in practice, most systems are of this type, are of hybrid nature. So you have a combination of continuous and discrete dynamics. So we talked about how to both model those systems and how to simulate them. So we will come back to that, talk a little bit more about it. And we looked a little bit about how you can model those in Simulink, but also how it can be done in Modelica and Simscape. So senior behavior is something a problem that shows up when you try to simulate hybrid systems, which can be a real problem if you can accidentally make a system that has this senior behavior. So basically that you will have an infinite number of switches in finite time, and that causes problems for the simulation environment because you can't really simulate beyond a certain time. And actually the system is not even defined after that time. And then we saw that you have, when it comes to stability analysis, it's quite tricky. You can have switch between different stable systems and you get an unstable system, and you can also switch between two unstable systems and get a stable system, so forth. Okay, then we we also talked about realization, so embedded programming in C. So this was completely new to many of you. Some of you have seen it in previous courses in your bachelor. But this is just to get all of you to have a basic knowledge in this area. So how the system is interacting with the hardware through the interrupts, how memory management is done, in particular in C. And then you have also practiced now how to implement controllers using C. And in the previous hand-in, you focused on the processes and threads, how you can synchronize different threads with semaphores. And when you have multiple threads, you have race conditions. So they, for example, if two threads share some memory or so, you can have problems with the updates, so then you need to protect the updates with mutual exclusions, and when you introduce mutual exclusions, you might introduce deadlocks, and then you need to avoid that. And we also explained how the scheduler in a typical real-time operating system works, and the problems with priority inversion and how you can solve that using priority inheritance. And in the guest lecture earlier this week, we had Sajid talking about the development process, especially large scale. What are the problems for those? Why do you need continuous integration, etc.? And what so especially when you do testing, you always need to do testing, of course. And the trick here is that you would like to automate as much of the testing as possible, because that is a real time saver. And then you need to have formal specifications, and then we talked about linear temporal logic, which you have already seen now in the discrete event systems course, but here we saw how it can be then extended. So Johan talked about this, how Volvo is using now an extension of linear temporal logic called signal temporal logic, to model properties for the type of for control systems, basically. So we extend linear temporal logic to include continuous variables, real variables, and that you have specifications over time. It's also good to know, Johan mentioned it, that the difference here in comparison to what you did in the discrete event systems, where you basically did model checking or supervisory control, there the assumption was that you only had finite state systems. So as soon as you introduce controllers and you have physical models, you have systems with an infinite number of states. So then the methods that you learned in the discrete event systems are no longer applicable. It doesn't mean that they are not useful, because you can still solve many important problems with them, but it's just then when you look at the closed loop system, you can't use those because you can't really enumerate them. So of course what you can do is that you can try to compute approximations of the real dynamics. You can do over approximation or under approximation of the behavior and get something that is discrete and then do the analysis on that. Or you have to do something like testing. So what Johan talked about is that basically that you have to it's really persistent.
You talked about?
What did I talk about?
What John talked about. We started with that. We were talking about the finite systems.
Yeah, the finite. So with testing, so you assume you can simulate the system, and then you can get the outputs, and then you can evaluate the outputs with respect to the specifications that you have. And the trick that Johan was doing was then, so he did automatic test case generation, and that means that you basically make a guess on the inputs, and then you simulate the system, get the output, check with your specifications, and then you apply an optimization procedure. So then you try to change the inputs in such a way that you're more likely to violate the specifications. So if possible, of course, because it might be that the specification always holds, which is what you really want. But if there is a chance that you can have a combination of inputs in such a way that the specifications are violated, you would like to find those as earlier on in the development process as possible. So, and the earliest phase is when you have the model only. So you have the control code and you have a model of the physics. And this is, so that's one advantage. So you have it early, but you can also scale it up. So you can put that on a cluster computer. So you can have tens or hundreds of different computers that try to do testing, which is much, much cheaper than try to involve the real hardware, which doesn't really scale in the same way. But I was, so the difference between testing and model checking is that we have in testing, in the kind of testing that we do, we do it because we have an infinite number of states in our system. But if you would like to do model checking, you have a finite number of states in your system. And very simple properties, like, for example, checking if a state is reachable, is not even a decidable problem for these type of infinite state systems. So if you have a control system, you would like to see, can I reach this state? So in general, you can't have an algorithm that will say yes or no for this. So there will always be an answer that or there will always be problems where it will say, I don't know. And then, if you have that property, they are not decidable. So this might, of course, also be interesting for you to know. I will not pose questions on modeling of quadrupeders or rotation of rigid bodies. So that is examined in the report that you have written. Or syntax for Simscape or Modelica or something like that. Yeah. So what we have tried to do in this course is to set it up in this way. So you start with the modeling and simulation. So here you apply your knowledge from the previous courses on the quad rotor system, and then you have used your knowledge on the control system design. You actually didn't learn much new here, but you had to apply your knowledge. And then you did both, you generated the code on the real-time system, and you had to evaluate the performance. And what you're doing now is that you also implement it in C. And to do this, you also had to know a little bit about what is the platform that the code is executing on. So what does the real-time operating system look like? So here we talked about all these problems that we mentioned before. What we haven't talked so much about is the communication aspect. So of course this is in most systems, like Sadir mentioned, in the SSY190 there are, what did he say, 120 ECUs, something like that, and you have a number of different networks. So of course communication is a very important problem as well. But we talked about the problems that communication leads to. So you have the delay, you don't know when to access the network, so that causes both jitter and latency, and that will affect the control performance. And then we ended the course by talking about this specification, testing, and verification. So yeah, you haven't really done any, we haven't been able to introduce this in the course yet. We had tried it last year, but there are problems with the Breach Toolbox on Windows 10, so it didn't work out very well, so we decided to exclude it for this year. So this was, I hope at least you got an idea about how this can be done, and that is really useful. And then we will see. We might have design projects where you can experiment more with these things. Yeah, so and Sadir also talked about this, the V model. So you should have heard about the V model when you leave Chalmers, about this, that you start with the specification and the requirements of the system, then you do the architectural design, and then you do the implementation, and then you try to test each individual component by itself, and then you basically integrate different components, and you do integration testing, and then you do final testing on the full product to check, for example, safety requirements and etc. And as Sadir mentioned, this is the tricky side. This is where you spend most of the time. And this is becoming more and more complex since the systems you have more and more different ECUs talking to each other, you have more and more complex control algorithms, you have more and more complex sensors, algorithms to analyze the inputs, etc. And this is probably the reason why we see accidents with autonomous cars, for example, because most likely the Uber accident had to do with the integration of different components and coordination of those. So not at this level, but on the integration level here. That's my guess, at least. Yeah. For next year, the course will also change name. So it will be called Model-Based Development of Cyber-Physical Systems, to stress this even more, because I think this is becoming more and more important in industry. So while it used to be focused on implementation only, now it's model-based. So model-based in the sense that you have models of the code and the plant and the requirements, and then you can evaluate everything on the closed loop system on the models only. And then typically what you would like to do is to combine this with code generation. So you don't have to write the code yourself, but you can rely on these high-level tools to do it. But we also, so in this course you now do both, right? So you do the code generation and you write the C code. And the reason why we do that is that I think it's good, if not only for pedagogical reasons, to have actually needed to dive into the code. And there are, I can also mention that in a real project there are a large part of the code that you can generate code for, but typically you also have to write C code around to connect with other parts that are developed in other ways. I think Sajid also mentioned that it depends a little bit on the nature of the code, if you would like to code generate it or if it's more natural to write it directly in C. So it's good to have, so C is the standard, C or C++ is the standard language that all these high-level tools, they compile or translate the code down into the C code, and then you have a compiler to generate the machine code. And of course the advantages here, it's important to understand this, that if you can build model of the closed loop system, you can use the model to do the control design, but you can also do evaluation of the closed loop system very early on. And that's critical. The more early you can find bugs, the more cheap they are to fix. And while Simulink has traditionally been the language to describe physical systems, there is a strong tendency or trend to move to these equation-based modeling languages of the physical systems instead. So Modelica is the international standard that are supported by different tools, and then Simscape is the dialect of Modelica but in the MathWorks toolchain. So, and they also support this visual representation, and you can have different pre-made components of physical systems, and you can just then connect them together. So it also speeds up the development a lot. We talked about the C code generation. So this is basically summarize what are the main advantages with model-based development. And then I mentioned that the new course name will be Model-Based Development of Cyber-Physical Systems. So with cyber-physical systems, we just mean that we have this whole, we have the computers, and we have the physical system, and that we also have networked computers. So they are distributed. But these systems are really hard to deal with, because you have very many different aspects that you need to deal with. So you have the different algorithms, you have different sensors, you need to, and you have the real-time operating system, and you have timing requirements on the system, and it's very heterogeneous in the sense that you have software, hardware, computer networks, etc., and you need to analyze all these things together. And so this is basically what shows up in practice, but then, so what is really the theoretical background for analyzing these systems? And that is the hybrid automata. Because with the hybrid automata, we can combine this, that you have the different states, the different continuous dynamics, and then you have the different states that you switch between. So, and that's why we started with talking a little bit about hybrid automata. Not very in-depth, but at least to get some basic understanding of how to build up models and what are the problems you get when you have hybrid systems. So we talked about this bouncing ball, and there are a number of problems when you try to implement this. We did show how to do it in Simulink. And then we switched over to Modelica to do it. And saw the advantages with using Modelica. So as I mentioned, there are basically two problems. One has to do with that you have the Sinu behavior. So if you make an ideal model, which this is, basically the bounce doesn't take any time. So it means that the bounces, they will become closer and closer to each other. And there will be some final time where we will have, so within the final time we'll have an infinite number of bounces. So of course, if you try to simulate an infinite number of bounces in finite time, you will have problems. So basically it means that the model is not defined beyond this time. So actually it's more fair to say that it's not only a simulation problem, but it's a problem of the model itself. And when it comes to the model, this particular example, the model is not really reflecting what's going on in reality. Because in reality, the bounce will take some time. So it will not have an infinite number of bounces in finite time. And another problem with these type of systems is that when we simulate them, we have variable step size. And this showed up like this. So it will try to, because at this point, so this is the height equal to 0, we should do a bounce, right? So we should change the dynamics here and the states. But the system has discretized time, and it might be that this is the height at step k, and this is the height down here at step k plus 1. And if we should do the switch here, we will have problems, right? Because we basically need to figure out that it was at this point in time that this condition for switching state happened. So if you're not really careful in the simulation, we might have examples where we see that the ball will bounce through the floor. So then, yeah, and in this example, it's obvious to see that there is something wrong with the model. But if you have a huge Simulink diagram with thousands of different blocks, it might not be so obvious to see that the model is apparently doing something that is not really reflecting what's going on in the physical world. So it's very important to be aware of these problems. And you have different settings in the simulator that you can that can help you to some extent at least to deal with these problems. So and then we switched over to introduce these Modelica and Simscape tools and equation-based modeling. And the reason for using this is, of course, that you can write your models in a way that is much more natural to you as engineers. Basically, you can look up the equations as they are written in the textbook and put them into the simulation tool. So you don't have to convert them into some standard form and try to solve them. And this is a huge time saver, and it's also means that you will have a lot more, it will be much more easier to reuse your different components that you have defined using these equations, because you haven't defined what are the inputs and outputs, you just defined the equations, and then the system will from this decide what are the inputs, what are the outputs from the context. Yeah, so this is a huge time saver, very important which of course is important in industry. So we talked about Modelica and SimSkate here, and you had to apply it in the project. Yeah, not go into that. So then the implementation in C. So what can you expect on the exam? So I would like you to understand how you the difference between when variables are allocated on the stack and when they're allocated on the heap, and the difference between having a variable that stores a value and a variable that stores the address to a variable. So basically pointers in C. And you should understand how you call a function by passing the value or by passing the reference to a variable. A typical exam question could be that I give you some C code and then I ask you to what is printed out or something like that when this is executed. So you should be able to read and understand C code for at least for those aspects that we have brought up in the course. What else? Yeah, you should understand what a stack is. How is memory allocated? When it's added in the main memory, when it's allocated on the stack. Why do you need dynamic memory? So you allocate memory on the heap, etc. So these things are important. And this stack concept is of course very much related to how functions are executed. So we talked about recursion, where a function will call itself, for example, and then the local variables inside the function are allocated on the stack. So you can have many different versions of that variable on the stack. So I think if you have understood pointers, you have understood recursion and what's going on when functions call functions, what are happening with the variables, then you know a lot about C actually. So I'm not expecting you to be able to write long C programs with correct syntax. You might be asked to write some implementation of something, but the syntax is not the most important thing if you forget the semicolon or something like that. But then that's why you also have this this technical report on Essential C, so you can look up the syntax there. But basically, to have being able to read and write small C programs. So are there questions about the C part? Or what is expected from you? So we can go through this example again. So we have a main method here, and you get arguments inside here they are filled in basically by the operating system. And they are put on the stack here. And you have a local variable here, float p, that initially is undefined. And then this function will call another function, pow. It will have some arguments here, they will also be put on top of the stack here. So you will have 5 and 1. And then when this code starts to execute up here, so it has two cases here. So it has the base case that will check if the exponent is equal to 0, then it will return 1. Or it will return something, the argument x times, and then it will call the same function again, but now with different arguments here. So it will decrease the exponent by 1. So initially the exponent was 1, and now it will call pow again with the exponent decreased by 1, so the next time it will be 0. So when pow starts to execute the second time, it will execute with these parameters, and they will be on top of the stack now. So the code will always look at the parameters that are on the top of the stack when it's executing. So, and in this case, we see here that now look up exp, and exp will be 0, so it will return 1. So that will be also be put on top of the stack when it's returning. So then when it comes back here, it can multiply x with what the pow function did return. So it will return 1, be on the top of the stack, and then it will now return 5 times 1. So it will be return 5, put on top of the stack, and it will remove the other variables, they are no longer needed now. And then float p will be equal to 5. So this could be a typical exam question to answer. What will be printed out by executing this code? So, and then of course we could have variables and pointers to variables. So we have the addresses and different tricks on doing that. And of course the semaphores as well, so we have talked about. So I hope it will still be reasonable, so don't be too worried about this.
A question.
Yeah?
What is P in the bottom of the stack in this case?
I think yeah, in this case, I don't necessarily, I'm not really into C, because this is usually not something you have to worry about. You just need to understand how this works. But from my understanding, this can be done in different ways. So if you should allocate the variables inside the method before you allocate the arguments, or if you do it in this order or vice versa, both will probably work, but you just have to decide on that when you link different code together where they should be. So so I don't think it must be done in this way. So, and this is also, if you should take the last argument first or the first argument first, for example. So there is just some convention used here. Okay. So then we had real-time systems. And a real-time system is what typical control systems are. It does not only matter when we compute the result, or sorry, what the result is, but also when we compute the result. Right? So control systems, it does matter when the control signal is computed. Right? So yeah, a real-time system is one whose logical correctness is based on both the correctness of the outputs and their timeliness. And then we talked about soft, hard, and firm real-time systems. So in soft real-time systems, it's not that critical. Nothing will really become a disaster if you don't meet the time constraints that you have, which is the case for hard real-time systems. But control systems, they are typically firm real-time systems. So it might be okay to miss 1 or 2 deadlines, but you don't want to miss too many. And as we talked about that, the more unstable the system is, the more hard it might be, because the system is basically running in open loop between the time instance when you compute your control signals. So if it takes too long, really bad things might happen. So with that, then we will go into the real-time systems and semaphores. But I think we can take a 15-minute break now and then